Hendrik Wade Bode, while working at Bell Labs during the 1930s, made significant contributions to circuit theory and control theory. One of his key achievements was the creation of a straightforward yet precise method for graphing gain and phase shift plots, now commonly referred to as the Bode gain plot and Bode phase plot. While working on the challenge of crafting stable amplifiers with feedback for telephone networks, Bode introduced the Bode plots as a graphical design tool. These plots effectively demonstrate the necessary gain margin and phase margin required to uphold stability amidst varying circuit characteristics due to manufacturing or operational changes. The concepts originating from Bode's work found application in the design of servo mechanisms and other systems governed by feedback control. Notably, the Bode plot exemplifies frequency domain analysis principles. The Bode plot for a linear time-invariant system includes two parts, a magnitude plot and a phase plot. The magnitude plot represents the function absolute value of h of s equals j omega in terms of frequency omega along a logarithmic omega axis. The magnitude is shown in decibels using the formula 20 times the log base 10 of the absolute value of h. Meanwhile, the phase plot depicts the phase, usually measured in degrees, of the argument of h of s equals j omega as a function of omega. Both plots share the same logarithmic omega axis, but the phase values are displayed on a linear vertical axis. A Bode plot is a graphical representation that shows the frequency response of a system. Consider a linear time-invariant system with the transfer function h of s. Imagine this system receiving a continuous sinusoidal input with a frequency represented by omega, where u of t equals sin A of omega t. As this input continues from an infinite time to a specific time t, the output appears as y of t equals y0, sine of omega t plus phi chi. This results in a sinusoidal signal similar to the input but with a phase shift phi and amplitude y0. Analysis reveals that the magnitude of the response, y0, equals the absolute value of Hjo, and the phase shift, f, equals the argument of Hjo. Essentially, when confronted with an input of frequency O, the system retorts at that identical frequency, amplifying the output by Hjo and altering its phase by arg, Hjo. These distinctive quantities ultimately delineate the system's frequency response, encapsulating vital information showcased in the Bode plot. Let's consider a scenario where an engineer at a fictional aerospace company is tasked with analyzing the stability of an aircraft autopilot feedback control system to ensure it maintains steady altitude without oscillations. They use a Bode plot to assess the frequency response and stability margins of the system. In this example, the frequency response of a second-order system is plotted to help the engineer understand how the autopilot system will react under different frequencies, which is crucial for ensuring the system's stability and performance. In this example, the frequency response of a second-order system is plotted to help the engineer understand how the autopilot system will react under different frequencies, which is crucial for ensuring the system's stability and performance. Let's consider another example. A robotics engineer is developing a precision robotic arm for an assembly line, and they need to ensure the arm's PID controller handles various load conditions smoothly without overshoot. The engineer uses a Bode plot to analyze the open-loop frequency response of the system, including the effects of different load conditions represented by various plant transfer functions. The plots illustrate how different loads, plant transfer functions, affect the frequency response of the system based on a PID controller. In this next example, an audio engineer is designing an advanced multi-channel electronic equalizer for a high-end sound system. The system needs to process audio signals with different characteristics to achieve optimal sound balance and clarity. The engineer analyzes the open-loop frequency response of bandpass and notch filters across multiple channels to ensure that specific frequency bands are enhanced or attenuated accurately. In practical scenarios, one can often simplify detailed Bode plots by utilizing linear segments that act as asymptotic representations of the actual response curve. Each component of a multi-element transfer function can be represented by a series of straight lines on a Bode plot, facilitating a graphical determination of the overall frequency response. Before the widespread availability of digital computers, engineers extensively relied on graphical techniques to minimize the requirement for tedious computations. These methods helped in pinpointing viable parameter ranges for new designs. The fundamental concept behind a Bode plot lies in the ability to decompose a function of the shape f of x equals a times the product of x minus c sub n raised to the power of a sub n into the sum of the logarithms of its zeros and poles. The equation is log of f of x equals log of a plus the sum of a sub n, log of x minus c sub n. This principle plays a crucial role in plotting phase diagrams explicitly. When drawing amplitude plots, this concept is implicitly used. By employing dB equals 20 times the logarithm base 10 of x to express decibels, amplitude in decibels is typically depicted. When dealing with a transfer function represented as h of s equals a times the product of s minus x sub n to the power of a sub n divided by s minus y sub n to the power of b sub n, where x sub n and y sub n are constants, s equals j omega, a sub n and b sub n are greater than 0, and h is the transfer function. The slope of the line in the amplitude plot changes at zeros and poles. At values of s, where omega equals x sub n, which is a 0, the line's slope increases by 20 a sub n dB per decade, and at s, where omega equals y sub n, which is a pole, it decreases by 20 a bb sub n dB per decade. The initial point and slope of the graph are contingent on the boundary conditions. To address irreducible second-order polynomials, you may approximate a x squared plus bx plus c as open parenthesis, a square root x plus ce close parenthesis, squared in various scenarios. Zeros and poles occur at specific omega values corresponding to x sub n or y sub n. Since the magnitude of h of j omega is a complex function denoted as the magnitude of h of j omega equals the square root of open parenthesis capital H times capital H close parenthesis. Therefore, at locations where a 0 or pole occurs with the term open parenthesis s plus x sub n close parenthesis, the magnitude of that term equates to the square root of open parenthesis x sub n squared plus omega squared close parenthesis. To correct a straight line amplitude plot, one should place a point 3 times the value of a ndb above the line at each 0 and a point 3 times the value of bndb below the line at each pole. These points should then be connected with a smooth curve, using the straight lines as asymptotes. It is important to recognize that this method does not address the handling of complex values for xn or yn. In scenarios involving an irreducible polynomial, the recommended approach is to determine the magnitude of the transfer function at the corresponding pole or 0, and position a point above or below the line accordingly. When dealing with a transfer function in the form h of s equals a product of s minus x sub n to the power a sub n divided by s minus y sub n to the power b sub n, the approach involves creating individual plots for each pole and 0, then combining them. The phase curve denoted by phi of s equals negative arctan of the imaginary part of h of s divided by the real part of h of s represents the actual phase. To sketch the phase plot for each pole and 0, if a is positive, commence the line at 0 degrees with no slope. If a is negative, start the line at negative 180 degrees with 0 slope. When the total number of unstable zeros and poles is odd, increase the starting point by 180 degrees. For every omega equals absolute value of xn, for stable zeros where negative real part of ze is less than 0, elevate the slope by 45 times an degrees per decade, initiating 1 decade prior to omega, equals absolute value of xn, for example, absolute value of xn over 10. At each omega equals absolute value of yn, for stable poles where negative real part of pib is less than 0, reduce the slope by 45 times bibn degrees per decade, starting 1 decade before omega equals absolute value of yn, for example, absolute value of yn over 10. Unstable poles and zeros in the right half plane, where the real part of s is greater than 0, exhibit opposite behavior. The slope is flattened once the phase has shifted by 90 an degrees for a 0 or 90 bn degrees for a pole. Following the plotting of each line for every pole or 0, amalgamate these lines to acquire the ultimate phase plot, which is the culmination of the individual phase plots. To construct a straight line plot for a first order, also known as one-pole, low-pass filter, begin by examining the normalized form of the transfer function. This function is in terms of angular frequency and is expressed as follows. H of j omega equals 1 divided by the quantity 1 plus j omega over omega sub c. The magnitude plot in decibels can be expressed using the decibel gain formula. A sub v in decibels equals negative 10 times the logarithm of the quantity 1 plus omega squared over omega sub c squared. This expression describes how the gain changes with frequency, providing a way to represent the filter's behavior in decibels. Here is a visual example of a straight line plot. When plotted against the input frequency, omega, on a logarithmic scale, the Bode magnitude plot can be approximated by two distinct lines. The first line, which represents angular frequencies lower than omega c, is a horizontal line at 0 dB because the term omega over omega c is negligible at low frequencies. This indicates no attenuation and a unity passband gain, meaning the output amplitude equals the input. The second line, representing frequencies greater than omega c, has a slope of 20 dB per decade. At high frequencies, the omega over omega c term predominates. These lines intersect at the corner frequency, omega c. Beyond the corner frequency, attenuation increases with frequency, reducing the output relative to the input. The phase Bode plot is created by plotting the phase angle of the transfer function, given by the formula. The argument of HLP at j omega equals negative inverse tangent of omega over omega c against omega. For frequencies much lower than the corner frequency, the ratio of omega to omega c is small, resulting in a phase angle near 0. The phase angle increases and reaches 45 degrees when omega equals omega c. As the ratio increases for frequencies much higher than the corner frequency, the phase angle gradually approaches 90 degrees. The phase plot uses a logarithmic scale. In both the magnitude and phase plots, the horizontal frequency axis can be replaced with the normalized frequency ratio omega over omega c. This conversion makes the plot normalized, eliminating the need for frequency units, since all input frequencies are now shown as multiples of the cutoff frequency omega c. Bode plots are useful tools for evaluating the stability of negative feedback amplifiers by analyzing the gain and phase margins of the system. In a negative feedback amplifier, the gain with feedback, denoted as AFB, is defined by AFB equals AOL divided by the sum of 1 plus beta AOL. Here, AOL represents the open loop gain, and beta is the feedback factor. The open loop gain, AOL, is frequency dependent and includes both magnitude and phase components. To prevent instability, the product of beta and AOL must not equal -1. This adheres to the Barkhausen stability criterion, which specifies that the phase must be 180 degrees and the magnitude must be unity. Through Bode plots, engineers can determine how close an amplifier is to a critical condition by identifying two essential frequencies. The first frequency, called F180, indicates where the open loop gain crosses the phase of 180 degrees. The second frequency, known as F0 dB, is where the magnitude of beta AOL equals 1, equivalent to 0 dB. The gain margin measures the proximity to instability by looking at these frequencies. By locating the frequency F180 on the Bode phase plot, the magnitude of beta AOL is assessed. If the magnitude at this point is greater than or equal to 1, the amplifier is considered unstable. When the magnitude of beta AOL at 180 degrees is less than 1, the system remains stable. The gain margin is calculated as the difference in decibels between the magnitude of beta AOL at 180 degrees and 1. Another key stability indicator is the phase margin. This is determined by identifying the frequency where the gain crosses 0 dB on the Bode magnitude plot. At this point, the phase of beta AOL is assessed. If the phase at this frequency is greater than 180 degrees, the amplifier is considered stable. The phase margin measures how much the phase at this point is above 180 degrees, indicating the closeness of stability. A straightforward stability criterion states that an amplifier is stable if the frequency at which the gain is 0 dB, F0 dB, is less than the frequency at which the phase shift is 180 degrees, F180. However, this criterion is only dependable for amplifiers that adhere to certain restrictions on the positions of their poles and zeros. When these conditions are not fulfilled, other methods like examining the Nyquist plot might be required. Additionally, the Neven-Linna-Pick interpolation theory provides a means to determine the optimal gain and phase margins for such systems.